Now, finally, on to thin film interference. You've seen thin film interference all around you, but you may not have known how to explain what you were seeing. Whenever you see an oil slick on water or a droplet of oil dripped on wet pavement, as in these two right-hand diagrams, you're looking at the swirling colors caused by thin film interference. Likewise, the colors you see reflected off a soap bubble arise from thin film interference. Or, whenever precision optics are required, manufacturers frequently coat the lenses or glass with an anti-reflected coating, another application of thin film interference, as in this pair of binoculars here, or likewise here in this instrument panel, in which they have coated optics on the right and non-coated optics on the left. Telescope makers and lens makers will sometimes use Newton's rings to determine how well their optics grinding is going, the rings being caused by thin film interference. On the left you see a diagram of a lens that has not been very well ground. If it had been completely well ground, the rings would be completely concentric, as in the diagram that's shown on the right. In all these applications, light gets reflected from two surfaces, and that reflected light, the two beams of reflected light, can interfere to produce maximal and minimal intensities. How does that work? It turns out to be an application of light wave interference, in which the extra distance that one beam travels compared to the other, something we'll call the optical path difference, determines whether there is constructive or destructive interference. It also depends on the relative indices of refraction of the incident and reflecting surfaces, and so the analysis is a bit involved. Let's dive in and describe it. Your authors summarize thin film interference in the text, and I'll follow their discussion generally. It turns out that there's an important omission that they have not included that we'll need to add to make the analysis complete. Let's first of all make some simplifying assumptions. First of all, let's assume that we're only interested in light that hits the film at normal incidence, directly, head-on. To simplify it even further, let's assume that we're only interested in one wavelength of light, and that's a very important assumption, monochromatic light that we're looking at. It turns out that we're going to have to pay attention to phase shifts, or the lack of phase shifts, when light reflects from the top surface and the bottom surfaces of the film. Remember that waves undergo a pi phase shift if they reflect off of a hard boundary, but there's no phase shift if the reflection happens off of soft boundary. For light, the hardness or softness of the boundary depends on the relative indices of refraction of the materials that meet at the boundary. The higher the index of refraction, the harder the boundary is to the light wave. So now let's assume that I have an incident light wave, which I'm going to show a little bit at an angle, even though we're making the approximation of normal incidence. That's going to make it easier to sketch the diagram. When that light gets to the surface, the top surface of the film, then some of that light is going to reflect off of the top surface. Some of that incident light is actually going to make its way through the film. When it gets to the bottom surface of the film, then it meets another boundary, and some of that light gets reflected from the bottom surface of the film. That light that's reflected from the bottom surface is going to travel back up, and it is going to interfere with the light that reflected from the top surface. Just to carry this on forward, there's going to be some of the light, hopefully most of it, that's actually going to make its way all the way through into the material in question. So most of the light's going to pass into medium 3, but we're interested in the light that reflects from the top surface of the film back into medium 1, and then the light that reflects from the bottom surface of the film and travels back up so that it passes back into medium 1 as well. And it's those two beams in this diagram, the purple beam and the blue beam, that we're wanting to look at the interference pattern of. Let's determine what is called the optical path difference that the blue beam travels that's greater than the purple beam. The first beam hits the top surface of the film and reflects. That's the purple wave. The second beam passes through the film, hits the bottom surface of the film, and reflects. That's the blue wave. If the film is made of something other than air, then the wavelength of the light when it's inside the film is going to change while it's traveling through the film, and that must be accounted for, and that is the thing that your authors failed to mention in their analysis, but it's an important quantity for non-air films. Let's let the thickness of the film be called D. It's unfortunate that your authors have selected the letter D in this because we've used the letter D for so many other things, such as in the Young's double slit separation, or also in the work equation, D is equal to distance. But that's the letter that they've chosen, and so that's the letter that we're going to use. Now, the second beam travels a distance D to get down to the bottom surface, and then it travels another distance D to get back to the top of the film after reflecting. So it's traveling a distance of 2D beyond what the other reflected beam travels. And if the film has an index of refraction of n with a subscript f, nf happens to be equal to n2 in this consideration here, then we say that the optical path difference is equal to 2 times d times the index of refraction of the film. Okay? Now what about the conditions for constructive and destructive interference? We first have to determine the relative phase shifts that the two beams may experience during reflection. If both beams experience the same phase shift during reflection, then constructive interference is going to occur when the optical path difference is equal to an integer number of wavelengths, and destructive interference happens when the optical path difference equals a half integer multiple of wavelengths. So we can write these relationships for constructive and destructive interference when the relative phase shifts are the same. Now, what happens if the relative phase shifts are different from each other? Then constructive interference is going to occur when the optical path difference is a half integer number of wavelengths, and destructive interference happens when the optical path difference is an integer number of wavelengths. So we can write a similar sort of expression for different phase shifts upon reflection. It is this set of conditions here that governs thin film interference. And what ends up happening is that we have to pay attention to the kinds of surfaces that are involved and account for phase shifts when we're trying to determine maxima and minima when we're looking at thin film interference. Here's a diagram with an explanation about coating optical glass surfaces with anti-reflective film to enhance the light that makes it through the optical system. Sometimes these coatings are called quarter wave coatings because the thickness of the films are 1/4 of a wavelength in order to minimize reflection. To start with, incident white light hits from air, usually. Say this is light that's coming in to a photographic camera, and we're trying to get as much light to the film plane as possible. So the index of refraction of air is 1.00. I'm eventually going to send that light through a glass lens, and frequently the index of refraction of glass is around 1.5. I put some thin film on here, and the thin film is about 1/4 of a wavelength. And the index of refraction of film is somewhere in between the index of refraction of air and the index of refraction of glass, so that I'm going to get a phase shift on reflection here and a phase shift on reflection down there. So light reflecting from both the top and the bottom surfaces of the coating undergo a 180-degree phase change, equivalent to shifting both waves by half a wavelength. The light that's reflected from the bottom surface travels an extra distance of half the wavelength of green light. In other words, what's happening is the optical manufacturers are adjusting things for green. Green happens to be in the center of the visible spectrum, and so they choose a wavelength and they say we're going to maximize things for green light. The green light reflected from the top surface interferes destructively with green light from the bottom surface. In other words, all the green light and most of the light in the middle of the visible spectrum is transmitted. So some red and violet light is reflected and the coating looks purple. So if you look at many very fine cameras, you'll see that there is this kind of purplish hue to the lens, and that's because it's been coated with this anti-reflective coating. Finally, let's work numerical example 74.3. Two pieces of flat glass are separated by placing a very thin wire, Why they used a wire, I don't know. Maybe a hair would be better between them, as shown in the diagram. Green light of wavelength 540 nanometers falls perpendicular to the top glass. A. What is the minimum separation of the glass pieces for maximum to occur? And B. What's the minimum non-zero separation of the glass pieces for a minimum to occur? All right, so here's what's going on. Incident light is coming in. The film is made of this air that's in between the glass plates. Light is going to reflect from the first surface of the top surface of that air, and then some light's going to pass through and reflect from the bottom surface of that air. And it's these two waves that are going to interfere to produce maxima and minima. And we're trying to answer these two questions. Let's let the separation where the interference takes place, let's let that separation be D. Now if I look at what's going on with this first light, this red beam that reflects off the top surface is going to experience no phase shift because it is light that has come through this first surface of glass, which has a high index of refraction, and hits this boundary here where air begins. So there's no phase shift of that. On the other hand, if I look at this other beam, what ends up happening when it reflects from this surface down here is that there's going to be a pi phase shift because it's hitting a hard surface down there. So this one experiences a phase shift. Now the optical path difference is going to be equal to 2 times the thickness of the film, D, that's what we're looking for, times the index of refraction, in this case of air, because air is what's making up the film. And if I want constructive interference, in other words, I want a maximum to occur, then what I want is that the optical path difference is equal to m plus a half times lambda. And if I want there to be the minimum separation of the glass, I'm going to let m equal to 0 for minimum separation. So I'm going to say that 2d times n air is equal to 1/2 of a wavelength for a maximum to occur. Maximum in this case means that I'm going to get a bright fringe as a result of this interference. So let's solve that equation for D. And now I put in the numbers, and I find that the film of air has to be 135 nanometers thick in order to get a bright fringe. Now, what about a dark fringe, a minimum? Well, I must have that my optical path difference is equal to some integer number times lambda. And if I want the minimum non-zero separation, then I'm going to say m is equal to 1 for a dark fringe. So let me put in the numbers, and let's solve that equation for D and substitute numbers. I find that the film thickness has to be 270 nanometers if I'm going to get a dark fringe. So, just briefly reviewing, what we've discussed has been 3 topics that involve wave optics. We've discussed single-slit diffraction. We have seen that the single-slit diffraction equation looks very much like Young's double-slit equation, but with some important differences. We've examined diffraction gratings, and see the diffraction grating equation looks like the Young's double-slit equation, but we can't use small angle approximations. And finally, we've discussed thin film interference, and there's all sorts of things to keep track of with thin film interference, phase shifts, and optical path differences, but we have solved some numerical problems with this. For now, that's it.